All right, objective 2, using sequences in real-world situations. Now to introduce this, there is actually times where I don't know if you will personally encounter this, I personally have, to where I've had to use this type of math in real-world situations, and there'll be 3 example problems you work through where that actually gives you an example of how that might come into play. But me personally, when I was in strength and conditioning and I assigned workouts to different individuals, I actually did an example roughly of what you might encounter in that situation. But let's say I want this certain person to lift a specific amount of weight and then add a specific amount of weight each time to their workout the next time they do that lift. And I want to know what they're going to be able to lift on the 200th day if all goes as planned. It at least gives me a rough estimate of what kind of goal I can set for them based off of this type of math. And this is why these types of formulas, the explicit formulas, were created, so that you wouldn't have to sit there and repeatedly add 2 or repeatedly add 5 200 times to get your answer. You can just plug it into a formula. And so I actually have done that before, to where I've given a specific amount of weight, and then if they do this workout for, like you will see in this example, 8 weeks, and they add the same amount of weight each time, like 5 pounds each time, how much can they estimatedly lift 8 weeks from now? That type of thought process. So I have used this math just to say that there is times when I actually had to Google the arithmetic explicit formula in order to do this math, but I did use it in my master's program. So there's that. Anyways, objective 2, using sequences in real-world situations. If I was going to do example 1 and model how to do it, I would read it first. Your favorite aunt decides to give you 1 penny, a whole cent, beginning on October 1st. Each day she gives you double the amount from the day before. So she gives you 2 cents on the 2nd, 4 cents on the 3rd, and continues the pattern throughout the month of October. So there's 4 parts. Part A says, is this sequence arithmetic or geometric? How do you know? And what is the common difference/ratio? So there's a couple different things. Again, to determine if it's arithmetic or geometric, this is a very important skill. It didn't necessarily give me a table or a sequence like it usually does. So that's what I'm first going to draw, is my table. I'm going to have n and a sub n. And I'm actually going to just box it in to make it look nice. So n and a sub n. And then the first term is 0.01. Sorry, my smartboard's not working correctly. The second term, 0.02, just to represent this. Third term, it's going to double again, so 0.04. Fourth term, double of 4 is 8, so 0.08. Let's do one more. The fifth term is 0.116. So there's a table. Again, we practiced that skill before in objective 1, and it's necessary now because it just helps me visualize and helps me kind of see where to go with finding if it's arithmetic or geometric. So if it's going to be arithmetic, again, it needs to add by the same thing each time. So I'm going to try to test if it's arithmetic. I do the second term, which is 0.02, minus the first term, 0.01. That is 0.01. To test it again, I'll do the third term, 0.04, minus the second term, 0.02, and that is 0.02. 0.01 and 0.02 are not the same, so it is not arithmetic. Now, to test geometric, the common ratio, it has to be multiplied by the same. So the second number, 0.02, divided by 0.01 equals 2. To test it, then the third one, 0.04, divided by 0.02 equals indeed 2. So this sequence that I drew a table of, based off of the problem, goes up by a factor of 2 each time. And the other, so it is indeed geometric because it has a common ratio ratio of 2. The other word in the word problem, this won't always be there, but the word double should mean something to you, meaning that every time the next term happens, it's going to be double the previous term. So that can't be arithmetic because there's no number you can add to the previous number to have it double. It has to be geometric, meaning it has to multiply. And double means another word for multiplying by 2. So there's 2 ways you could have done it. I always like to do the math, this entire, drawing the table and then doing arithmetic, geometric, just because it won't always give you clue words like that in the problem. So that's part A. I found out it was geometric because it had a common ratio of 2. So if you write an equation then to represent this sequence, again, an equation all we're looking for is the explicit formula. There's one for geometric and there's one for arithmetic. Now, geometric just so happens that the other video you just watched for Objective 1 happened to be geometric as well. It won't always be, obviously, because you will encounter arithmetic situations. But the geometric default explicit formula is a sub n equals a sub 1 times my r raised to the n minus 1. And like I mentioned in the previous video, the only 2 things that change are your a sub 1, your first term in the sequence, and your r. So I'm going to write it in green, because I like green. Go Packers. Switch the a sub 1 and the r based off the math I just did in part A. So, a sub n equals my a sub 1, the first term in this situation is 0.01, times my r we just found out to be the ratio of 2 raised to the n minus 1. That is the explicit formula. The explicit formula is very important because that will help you find any term number that you want, and that's what it's going to help us find part C. How much money does your aunt give you on October 17th? Now, when you first read this, she begins with giving you a penny. That's pretty minuscule. You're going to think, that can't be a lot of money by the end of the month. But you'll be surprised because it's geometric and because it's multiplying or doubling each time, how quickly it grows. So, October 17th just represents the term. In this case, hopefully you guessed it, I want to know the 17th term. So I'm going to write n equals 17. Actually, hold that thought. Don't write that quite yet. What that means, hopefully by now you're catching on. Let's say I want to find the 5th term. N equals 5. So then a sub 5, if I look at my table, the n of 5 right here, a sub 5 is right here. So a sub 5 equals 0.16. The explicit formula allows us to just compute it without having to double it 12 more times. So hopefully by now, if I ask you what's the 5th term, you'd be able to tell me based off the table given to you. But in order to find 17th term, I'm going to write n equals 17, and a sub, not n anymore, a sub 15, 15th term, is going to be 0.01 times 2 raised to the... Now, the explicit formula is just a function. Anytime you're trying to evaluate a number, an input, 15 is the input, the output is the answer you get, 15 is the x, the output is the y. The input is the variable, it takes place of the variable. So I raise it to the 17. Instead of n, I'm going to put 17 minus 1. Notice the n changed here, a sub n turned into a sub 15, and the n changed here, n minus 1 turned into 17 minus 1. You might be confused, sorry. It's not a sub 15, it's a sub 17. But the n's changed to 17, so the n's changed to whatever number you're trying to evaluate. Alright, now we just do that math to find how much money you're going to get on the 17th day. 0.01 times 2 raised to the 17 minus 1. Just to double check something. Yep, you can put this right here exactly as you see it into your calculator. You could also write 0.01 times 2 raised to the 17 minus 1, which is 16. Either way would give you an answer of $655.36. Take a moment to try that on your calculator. Make sure you get $655.36. Now, that's pretty crazy. It doubled every day, and on the 17th day, she's giving you $655. You started at a penny. Now, consider investing money and how that works a little bit too. And we can talk about that later in the semester. But go ahead and try the next two examples of real-world problems.